So we present SurfsUP, learning fluid simulation for novel surfaces. So predicting how fluids interact with solid surfaces is an important problem with many applications in object design, for instance, designing aerodynamic cars, or in home robotics. Imagine asking a robot to get you a glass of water. It's also a challenging problem because it involves complex fluid physics, and also you want your method to be able to reason about potentially complicated and novel surfaces. So why learn fluid simulation for this problem? Well, it's faster and more general purpose than physics-based simulators, and also differentiable for solving inverse problems. So the current state of the art for learning-based simulation are graph neural networks, which represent the fluid as a system of particles and track the positions of those particles over time. So the particles are encoded into a graph, and then message passing is performed, which learns interactions, and then the one-step accelerations for each fluid particle are predicted at training time. Then, to roll out at test time, the accelerations are used to obtain updated positions, and then this proceeds iteratively. So the problem is that if you have a solid surface inside the simulation, this is also represented with particles inside the graph. But surface particles are lossy, they introduce artifacts, and they cannot scale to complex realistic scenes, and so this is really an open problem about how to scale to complex realistic scenes. So with the aim of finding a better way to represent surfaces inside a fluid simulator, we instead leverage implicit representations and particular sign distance functions. So if we look at the figure on the right, we see that as a fluid particle approaches the surface, really only the local region close of the surface close to the fluid particle is what is relevant for dynamics, and we argue that STFs provide a good local representation of surface geometry. So this is for a few reasons. One is that STFs have infinite resolution, so they can be queried at any point in 3D space. And secondly, they provide rich geometric information. So the value of the STF provides the distance to the closest point on the surface. The gradient of the STF provides the direction to that closest point. And so we leverage STFs in our proposed method for learning simulation. And so given a system of particles and a STF, we construct a graph of fluid particles, and to each fluid particle we add the value of the STF and the gradient of the STF at that particle's position, then perform message passing, and then predict the accelerations for each fluid particle. And the loss is weighted higher for particles that have a low STF value, i.e. that are near the surface. And that has the effect of penalizing errors and interactions of fluid near the surface more stringently. So at training time, our model only sees exact analytical STFs of shape primitives like spheres, cones, cylinders, and tori. And these shapes cover a diverse range of local surface geometry like curves, corners, and holes. And the key insight is that diverse local geometry plus STFs, which provide a rich representation of that local surface geometry, enables accurate dynamics in large, complex scenes that globally may look very different from the shape primitives at training time, but at a local level may look something like what has already been reasoned about in the training set. And so we exploit that principle of locality and dynamics using STFs for a successful generalization to large scenes. So results, SurfsUP is able to produce accurate, stable fluid rollouts for novel shapes represented as STFs, and you can see here that our simulator has high fidelity to the ground truth. So a key result is that we're able to generalize zero-shot to complex scenes. So we see, for example, here that we've trained a neural STF, a siren model on a room scene. That model generates our STF features, and SurfsUP is able to do accurate simulation in this much more complicated, larger scene than anything that it's seen during training, right? So it's able to support accurate simulation, and that compares, if we compare that to a baseline that represents the surface as particles, we see that the baseline in this case simply cannot represent the surface with the resolution required, and so the fluid simply falls through the surface. And so we also see here that our method can not only scale, but also handle fine structured geometry, like the coral scene here, where we're able to filter water through the coral tentacles accurately. If we compare that to the baseline is not able to support fluid simulation with fine structured geometry like the coral, and is unsuccessful at simulating this scene. So quantitatively, we compare to GNS, a state-of-the-art baseline which represents a surface with surface particles, and on a set of complex scenes for which we train neural STFs of objects. Across all metrics, we outperform GNS, so we have lower chamfer distance on the rollouts compared to the ground truth simulator, and also less surface penetration, so less particles penetrating inside the surface, which is a serious failure mode. So we make 2 points. One is that our method is more scalable because we scale with the size of the STF network instead of the number of particles, and our method is also more efficient because for the baseline there is a trade-off between performance and cost depending on the number of surface particles that we're able to overcome. And this is an example of a mountain scene for which our model is able to produce accurate realistic dynamics, which is 3 orders of magnitude larger than any scene that we had during our training. So please check out our website and our archive link, and please come visit our poster. Thanks very much.